two topics today. The first one, I still want to show you two more examples about good methods and bad methods. The second example, we turn to study section 1.1, Taylor's theorem. Through this course, we often use Taylor's theorem. Topic one, two more examples. The first example is I want to compute a determinant. Determinant is a number. The notation is this notation. It is a number. A number. This number determines whether the matrix A has inverse. If the number is 0, then matrix A has no inverse. Otherwise, A has an inverse. Now suppose A is an n by n matrix. A is n by n. A11, A12, A1n, A21, 22, 2n, and AN1, AN2, ANN, n by n matrix. To compute determinant of a matrix, we have a formula. The formula is, before I introduce the formula, let me introduce some notations first. Let me let Aij be the matrix obtained by deleting row I and column J of the matrix A. I use Aij below the submatrix by deleting the ith row and the jth column of the matrix. And then I let Cij below this number, negative 1 I plus j, negative 1 to I plus j, then determinant Aij. Then the formula to compute the determinant of an n by n matrix is, then the formula to find determinant A is, determinant A is equal to, look at the first row of the matrix. The first row, the first entry is A11. A11 times C11. C is defined here. This is C. And then plus the second entry, A12 times C12, and so on. The last term is A1n times C1n. This is the formula to compute a determinant. Say for example, suppose that A is 2 by 2. A11, A12, A21, A22. Now compute the determinant of this 2 by 2 matrix by formula. By formula, Look at the first row. By formula, it is A11 times C11 plus A12 times C12. C11 is -1 to the power is I plus j. Now I and j both are 1. So the power is 1 plus 1. Then times determinant of A11 plus the second entry in the first row, on the first row. It is A12 times C12. C12 is -1 to the power 1 plus 2 times determinant of A12. Now let me simplify this sum. -1 to 1 plus 1. 1 plus 1 is 2. So -1 to 2 is +1. So the first term is A11, determinant of this matrix. Then plus -1 to the power is 1 plus 2. 1 plus 2 is 3. -1 to the third is -1. So minus A12. A12, right? Okay. Then A11, by definition, is the matrix obtained from the matrix A by deleting row 1 and column 1. Delete row 1, delete column 1. So only this entry remains. So A11, this matrix is determinant of this matrix A22. Then minus A12 times determinant of this capital A12. Capital A12 is a matrix. To get the matrix, delete row 1, column 2. Row 1, column 2. So this entry remains. This is determinant of A21. Determinant. For 1 by 1 matrix, this is a 1 by 1 matrix. Determinant is just the entry itself. This is a 1 by 1 matrix. Determinant is the entry itself. Therefore, determinant of a 2 by 2 matrix is this number, A11 times A22 minus A12 times A21. A11, A22 are the entries. On the main diagonal line. A12, A22, A21 are the entries on the anti-diagonal. So a 2 by 2 determinant is the product of the main diagonal entries minus the product of the anti-diagonal entries. This is the formula to compute 2 by 2 determinant. As a second example, consider this matrix, 3 by 3 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I want to compute the determinant of this 3 by 3 matrix. By formula, determinant of this matrix is look at the first row. It is a A11 by formula times C11 plus A12, C12, A13, C13. A11 now is 1. A11 is 1. C11 by formula, -1 to the power is I plus j. And then determinant of this matrix, A capital A11. Then plus A12 now is 2. Then times -1 to I plus j. I is 1, j is 2. Then times determinant of capital A, 1, 2. Then A13 is the number 3 times -1 to the power is 1 plus 3. Determinant capital A13, capital A13. Now let me simplify this sum. -1 to 2 positive 1. So the first term is this. Second term, -1 to 1 plus 2, -1 to the third, negative. So minus 2 A12. Then third term, the sign is -1 to the fourth, positive 1. So plus 3 A13. Okay, for capital A11, I delete from the matrix A, row 1, column 1. So A1, capital A11 is part. So the first term is determinant 5, 6, 8, 9 minus 2. Determinant capital A12. Delete the first row, second column. What remain are 4, 6, 7, 9, and then plus number 3. Capital A13 is A13. Delete row 1 and column 3. Then the remaining numbers are 4, 5, 7, 8 determinants. Okay, now continue the computation. All the 3 determinants are 2 by 2 determinants. We have formula to compute 2 by 2 determinants in the previous example. The first determinant is product of the main diagonal entries, 5 times 9, minus product of the anti-diagonal entries, 8 times 6. Okay, brackets. And then minus 2. The second 2 by 2 determinant is product of the main diagonal entries, 4 times 9, minus anti-diagonal entries, and then plus 3. The third determinant is 4 times 8, minus 7 times 5. Calculator, it is 0. Because determinant of these 3×3 matrix is 0. This matrix has no inverse. These are the examples about the use of this formula. The problem with this formula is computational cost is very high. Okay. In general, to compute an n by n determinant by this formula, the number of multiplications, how many in general for n by n determinant? N minus 1 times n factorial. This is a very big number. Okay, now suppose I want to compute a 20×20 determinant. This is a very small determinant. In industry, in future, if you have a chance to work in industry, you will see that the size of determinants are usually very big, at least million by million. But anyway, now let me compute 20×20 determinant by a supercomputer. Okay. Now suppose I compute 20×20 determinant by using a supercomputer, by a computer. Okay, which can perform. How super this computer is? 10^10. 10^10 is 1 billion. 10^10 floating point operations per second. This computer is powerful. Okay, now let's see. By use the formula, this formula here, how much time, how long we need to wait for the result? Okay, about this formula, the computational cost is n minus 1 times n factorial. Okay, how long we need to wait to get the result? Okay, 20×20 determinant about so many n minus 1 times n now is 20 factorial. There are so many multiplications. Okay, the computer, I suppose the computer 1 second can perform 10^10 multiplications. So how long we need to wait? Divide this number by 10^10. We need to wait for so many seconds. Now, calculator. This number is about 4, 6, 22, 51, 38, 1/6 so many seconds. In hours, how many hours? Divide this number by 3,600 seconds. So how many hours? It is 1284,031.62. So many hours. How many days? One day has 24 hours. So I divide this number by 24. Then I get 53, 50, then 132. I need to wait so many days for the result. 1 year has 365 days. Divide the number by 365. Then I get 146.58 years. Clearly, if you use the formula to compute a determinant, almost it is impossible to get the result. You need to wait for over 100 years by a supercomputer. So clearly, the formula is a very, very bad method. Then usually, what kind of method we use to compute a determinant? By use Gaussian elimination. If you have a matrix calculator, how that matrix calculator compute a determinant? The calculator use Gaussian elimination. Very fast. To compute a 20 by 20 determinant, Gaussian elimination, just take 10 to the -7 so many seconds to get the result. So this is a typical bad method. Okay. Now, second example about good and bad method. Example 2. Example 2. Solve a linear system. Yeah. In industry nowadays, how many unknowns a linear system? 10 billion at least. So the matrix A, the size 10 billion. That's normal. Okay, A usually is large, very large, super large, and sparse. What it means, sparse. Most of the entries of the matrix A are zeros. For a sparse matrix, the storage is small. Why? Because we don't need to store 0 entries. We only need to store non-zero entries. So to store a sparse matrix, memory is cheap. Now to solve a linear system, this time Gaussian elimination is a bad method. Okay. Gaussian elimination is a bad method. Why? Take a look how Gaussian elimination works. Okay. 2 steps. Step 1. Perform LU factorization. Where L is a lower triangular matrix. U is an upper triangular matrix. Step 1, perform LU factorization. Then the matrix, then the linear system, let me give a name to this linear system, says a star. Then star can be written as L times U times X is equal to B. Now, let me denote U times X by 1. I want to get X. Then I can solve Ly is linear system. After I get Y, Y is equal to U times X. Then after I get Y, I solve this linear system. Lower triangular linear system, we can solve it by forward substitution. Very fast. Upper triangular linear system, we can solve it by back substitution, also very fast. These two steps together is Gaussian elimination. Then what is the problem about Gaussian elimination? The problem is the problem with Gaussian elimination is, okay, when A is sparse, the storage of a sparse matrix is cheap. When A is sparse, when we perform LU factorization on the matrix A, L and U usually are dense. What it means, dense. Most of the entries are non-zero. Yeah, dense. All the entries non-zero. All the entries non-zero. Now, step 2, we need L and U. So after we compute LU factorization, we need to keep matrix L and matrix U in order to perform step 2. But now, how many memory storage is to keep L and U? In total, N squared. So to perform, when you want to use Gaussian elimination to solve a linear system, your computer should be able to hold so many numbers. Should be able to hold so many numbers. But this is impossible when N is super large. When N is 10 billion square, super large. So almost no computer can have so many memory to store so many numbers. So therefore, Gaussian elimination, it is good in computing, in the computation of a determinant, but it is bad in solving a linear system. Now, the question is, Gaussian elimination doesn't work. Then what kind of method we usually use to solve a linear system? Iterative method. Yeah. In industry, we usually use iterative methods to solve a linear system. Iterative methods, storage memory, storage requirement is cheap. Just need to store the sparse matrix and a few vectors. That's it. Okay, this topic 1. In this topic, I show you 2 more examples about bad methods and good methods. Now, the second topic, we turn to study section 1.1. Taylor's theorem. Taylor's theorem. Okay. Topic 2. Section 1.1. Taylor's Taylor's theorem. Taylor's theorem has several forms. Taylor's theorem has several forms. Now let me present the first form today, and then in the next 1 or 2 lectures classes, I present the other forms. Let me introduce one notation first. I like this notation. C here means continuous. CM AB. Yeah. I let this notation be the set of all functions f for which each function has derivatives from order 1 to order m. Okay, for which first derivative, second derivative, until the nth derivative all exists and are continuous. This function has derivatives from order 1 to order m, and all the derivatives are continuous. Continuous on the open interval AB. Any examples? Say, for example, polynomial. For example, x to the third plus 2x plus 1. This is a function. This function has any order derivative. And after you take derivative, still polynomial. Polynomial still continuous. So therefore, this polynomial is in CM AB for any interval AB. One example. Second example, very easy to find examples. Say psi of x. Psi of x has any order of derivative. And also after you take derivative on psi, still continuous. So this is in CM AB for any it is psi defined on negative infinity to positive infinity. Yeah. And also here, a negative infinity to positive infinity in more detail. Yeah. After I introduce you this notation, then I am ready to present Taylor's theorem. Taylor's theorem has several forms. The first form is theorem. It is Taylor's theorem with Lagrange remainder. Okay. The formula is here. Okay. Suppose function f is from this set Cm plus 1 AB. That is, function f has derivatives of order 1 to order m plus 1, and all these derivatives are continuous on the interval AB. Then, for any 2 points, C and X, in the open interval AB, we have the following formula. F of X is equal to F of C plus 1 over 1 factorial derivative of C times X minus C plus 1 over 2 factorial F second derivative at C X minus C squared. Here, let me change the notation here. Don't use M, but use N. Let me use N. N here. N. Here is 1 over N factorial F derivative N times, then evaluate as C X minus C to the N. The left side is a function, a general function. The right side is a polynomial. A function and a polynomial, of course, they are not equal. So we need to add an error term plus error term. Say error E. N depends on N, also depends on X. Yeah. After we add an error term, then we have this equation. Then where? What is the error term? Where? The error term is equal to 1 over. The error term is similar to this term. It is 1 over N plus 1 factorial. Then times function f take derivative N plus 1 times evaluate the derivative at some point psi, then times X minus C and plus 1. Okay, where psi, usually we don't know the point psi, but we know that this point is a point between C and X. Yeah, we call this formula for the error term Lagrange remainder. And this equation is Taylor's theorem with Lagrange remainder. Also, let me give a term for the polynomial. This polynomial is called Taylor series. Just a term, okay? Now let me show you one example about this formula. Example. There are two parts. Part one, determine the Taylor series of this function f(x) is 1 over plus 1. Okay. Determine the Taylor series of this function. In the theorem, we have an interval AB. We also have a point C. With the interval AB be, let me see, level 1, 1. The point C is 0. Okay, now let me solve this part first. Solve solution. I need to compute derivative on this function. It's easy to see that take derivative on the function k times. The answer is level 1 to the k times k factorial over 1 plus x. The power is k plus 1. Then evaluate the derivative at the point C, right? Derivative at the point C, right? Point C. Now C is 0. So plug in 0 in x. Then we get level 1 k factorial, and then 1 plus 0 k plus 1. So the answer is level 1 to the k times k factorial. So therefore, by formula here, the Taylor's theorem, the Taylor's series is f(x) is equal to f(0) plus 1 factorial f derivative at 0 times x minus c. C now is 0, so only x, plus 1 over 2 factorial f second derivative, x minus c squared, so x squared, and so on. 1 over n factorial f derivative n times at 0 x to the n, and then plus the error term. Then plug in this formula here, plug in this result into the derivatives. Then I get 1 plus level 1 times x plus level 1 squared, x squared plus n xn, then plus error term. Okay, where the error term in detail is en x is equal to 1 over n plus 1 factorial. Derivative n plus 1. Then evaluate at some point psi. We don't know what psi is. We only know that psi is between c and x. Now c is 0. So psi is between 0 and x.
Professor,
Pardon?
could psi be x or c as well, or is it just strictly between the two?
Strictly between, greater than or less than, no equal.
Okay, thank you.
Yeah. Times x and plus 1. Okay, where psi is between, I don't know, x is greater than 0 or not. So what I can write is between 0 and x. Okay. Psi between means not equal. Okay, psi cannot be 0, cannot be x. Then I plug in the derivative. Yeah, plug in psi in x, then I get this derivative. So it is, let me write on the next page. So en x is equal to negative 1 n plus 1 over 1 plus psi n plus 2 x n plus 1. This is part A of this example. There is a second part, but I'm not going to present the second part because I don't have time. You can take a look at the second part in my notes. I post my notes on one course. So not difficult. Okay, not difficult. So take a look at my notes for the second part. This is all for today's class. Any questions about today's class?